7 to the power 2017. Nobody wants to calculate that. Probably not even a computer. If I just want to know what is the last digit, this is a standard problem that many people, many of you, may already be familiar with. I know you're familiar with it, but I still want to talk about the pattern of what happens if I take the last digit of a number raised to a power. Because from this pattern, we will discover a much bigger pattern that we'll cover in the rest of this course. So if I'm looking at the last digit of a very large power, it's easier maybe to think about what happens when I raise to smaller powers. So let's start to make a table. And the way I'll build this table is I'll write a 7 here, and I will write that this is to the power 1, so this is to the power 0, sorry. The way that I'm writing this table is that I will take what is 7 to the power 0, last digit, which is just 1. Here I'll write 1, 7 to the power 1, last digit, well, so far it's still just 7. 7 to the power 2, last digit, now I'll write 3 bars as congruent to, because the last digit is 9, 49. 7 squared is 49. For 3, if I want 7 cubed, again, because I have modular arithmetic, if I already know that this is 9, I can take 9 times 7. 9 times 7 gives me 63, and I can put the 3 there. And the last one I'll write here is 4, because 7 to the 4, if I want to do this, I take 3 times 7. 3 times 7 is going to give me 21. Why is this important? We already now see that it has repeated. 1, 7, 9, 3, 1. Once I have a 1, the next one, because always I just take what was the last one times 7, I will get back to the 7. So it will repeat. That's what happens with 7. Let's quickly check all the rest of them, because this is where we will see some interesting patterns. What are all the rest of them? Well, I could be asking about 0, meaning I multiply something by itself many times. This is a little bit tricky. 0 to the 0. Not sure what I want to put there. But the rest I'll put that these are all 0. Okay? Meaning if a number ends with 0. At that point you might say, as long as that number that ends with 0 is not 0 itself, you could say it's going to be 1. But I'll just put a little, I'm saying that's an unusual case. What if I have a number that ends with 1, and I want to know what are its powers? Well, that's very easy too. Those are just 1. If it ends with 1, all its powers will end with 1 also. How about 2? For 2, I will start by saying 2 to the 0. Well, that will be 1. Everything to the 0 is 1. And then 2 to the 1 is 2. 2 squared becomes 4. Then it becomes 8. Then it becomes 6. And then 6 times 2, 12. 6 times 2, 12. And so what I see here is that this has now a repeated pattern as well, because here's the 2. The little thing that's a little bit strange is that it's not quite a repeated pattern because of that 0 up there. Okay? I have 1, 2, 4, 8, 6, but then 2, and then it carries on again with 2, 4, 8, 6, 2. I'm emphasizing that the 0 is an unusual special case. What if I have 3? Well, again, 0 is an unusual case. But then I have 3. 3 squared is 9. 9 times 3 is 27. 7 times 3 is 21. And now it will continue with 3. And it will go on. Okay? What about 4? 4 goes 1, 4. 4 squared is 16. 6 times 4 is 24. 4 times 4 is 16, and then it goes 4 again. So I'm seeing a 4, 6, 4, 6, 4 pattern. What I'm trying to do here is show how all these different patterns come together. 5. If I have 5, it starts 5 to the 0, so 1, but then they're all 5. Anything ending in 5 raised to any power is 5, apart from 0. How about 6? Well, 6 again starts with this 1, which is strange. But then I have all the powers of 6. If I keep multiplying a number by 6, it just keeps the 6. Okay? I already drew my 7. So now let me go to the 8. 8 becomes 8, 8, 64. 4 times 8 is 32. 2 times 8 is 16. 6 times 8 is 48. Okay? And let's finish with the last one, which is 9. 9. 9 starts with 1. 9. 9 squared is 81. Times 9 is a 9. And times 9 is a 1. Times 9 is a 9. Okay. So now I have this big table. The important thing about this table is that it looks like there's some very strange things going on at the 0. That's not nice. But there's also a very nice thing going on at the 5. This entire row of 5 is exactly the same as this entire row of 1. Many people, when they do math competitions, get used to the fact that it repeats every 4. I want to say it is true, it repeats every 4, because when I do 1, 2, 3, 4, then the next one will be like 5, 6, 7, 8. This is a repeating block. So many people have just memorized, go every 4, it will work. Every 4, it will work. I drew the table to show you there's a little bit more than just every 4. You see, there are even some of these that repeat a lot, like 5, 5, 5, 5, 5, 5, 5, 6, 6, 6, 6, 6, 6, 6, or 1, 1, 1, 0, 0, 0, or this other one, 1, 9, 1, 9, 1, 9, 1, 9. So it is true that it repeats every 4, but there's also more inside. But why does it repeat every 4? Let's look a little bit more into this. The goal of the next part is to start looking at what makes things repeat. Here I'm looking at the last digit. The last digit is where I just look at what it is modulo 10. You can make 10 out of 2 and 5. If I'm interested in what something is mod 10, I can break it into what it is mod 2 and mod 5 using what we just saw earlier, the Chinese remainder theorem. Meaning, if I know what something is mod 2 and mod 5, I know what it is mod 10 also. So I should look at how this repeating pattern is happening, mod 2 and mod 5. So let's do this again. Now what I'm interested in doing is I want to draw this pattern, but I don't want to look at the last digit. I just want to look at what happens mod 2. Okay, so we'll draw the same table. This time, the table will be much simpler. I'll start with a 7, just because that's a nice general number to be trying. And I won't do 7 to the 0, because we already know 0 is strange. 7 to the 1. 7 to the 1, mod 2 is 1. It's odd. 7 squared mod 2 is still 1. This is maybe not that surprising. It looks like it's going to be very, very stable. 7 cubed is 1. Actually, all of these will be 1 here. What about the next column? If I'm asking about something like 3, what are all the powers of 3? Well, 3 to the 1, that's odd. It looks like what happens is the odd ones are just 1. Even ones? What if I have something like 4? Well, 4 to the 1, that's even. It's 0. But all the other powers of 4 are 0. What you've just seen here is that if I look at what something is mod 2, all the powers of it are the same as what it was before. This is actually part of a very useful fact, which is that x squared is always congruent to x mod 2. We can see it with our own eyes here, because no matter what I start with, I will just get x squared to be the same as x. Another way of saying this is that if I have an odd squared, it's odd. And if I have an even squared, it's even. Of course, if I know this is true for x squared, I also know this is true for x cubed, x fourth, and so on. Mod 2, multiplying and getting higher powers, does nothing. So if I'm wondering about my repeating patterns, what this means is that 2 has no effect whatsoever. And so the repeating pattern, the repeatingness of the pattern, comes only from the 5. Now let's look at the 5. Mod 5. Let's try doing the same thing again. So again, what I'm going to do is I'm going to take, let's start with 0. And the way this table will work is I'll put a 1 here. And here is 0 raised to the 1 mod 5. Well, that's 0. 2 is 0 squared mod 5, which is also 0. Actually, 3, 4, all of these are 0. Let me put a 5 here. Okay? All of these are 0. What happens if I have something that ends in a 1? Actually, I can already say the thing that I'm writing up here is not just the last digit. But what I'm writing up here is what a number is mod 5. So for example, this 0 also contains the 5. Because 5 and 0, if a digit ends, if the 5 is the last digit, it's 0 mod 5. Think about it that way. The 1 column, if I keep taking all of the powers, this will just be 1, 1, 1, 1, 1. The 2 column, if I look at all the powers, it is 2. 2 squared is 4. 2 cubed is 8. Times 2 is 16. And then here is, oh, sorry, just a second. I need to reduce everything mod 5. So 4 times 2 is 8, but mod 5 is 3. 3 times 2 is 6, mod 5 is 1. 1 times 2 is 2. Okay? Here is a 3. For 3, it goes 3. 3 squared is 9. But 9 I have to reduce. So I'm going to reduce 9 to mod 5 is 4. Now 4 times 3 is 12. Reduce gives me 2. 2 times 3 is 6. Reducing gives me 1. 1 times 3 is 3. And I'm almost done because the last possibility is 4. These are what the remainders are, mod 5. 4. 4 squared is 16. 16 gives me a 1. Now, 1 times 4 is 4. 4 times 4 is 16, which gives me 1. 1 times 4 is 4. I wanted to draw this so that we can see more patterns inside. First of all, you see that there's an alternating pattern 4, 1, 4, 1, 4, 1, 4, 1. There was also an alternating pattern on 9 before. 9, 1, 9, 1, 9, 1, 9, 1. It was right here. 9, 1, 9, 1, 9, 1. But why is that? The reason that is because 4 is the same as minus 1. So these are like minus 1 squared is plus 1, minus 1 cubed is minus 1, minus 1 to the 4th is plus 1, and so on. Other interesting things about this table. This last row is the same as this first row. That was the repeating pattern that we saw. It's exactly the same. And so what we actually see here is that if I take x and raise to the 5th power, this is congruent to x mod 5. That's interesting. Let me pull back. We saw something mod 2. We saw mod 2 that x squared was x mod 2. Interesting. X to the 5 is x mod 5. There's also something else here, which is almost good. All these ones. All these ones. What is going on here is this seems to say x to the power 4 is congruent to 1 mod 5 unless it obviously isn't. Mathematicians like statements like this, where there's an obvious reason why x to the 4th would not be 1. That would be because it's 0. I mean, if it's a multiple of 5, take any power, it's a multiple of 5. So this thing here is an obvious exception. But all the rest of them are all 1. There's another way to write this, unless it obviously isn't. Another way to write that same statement is to say, as long as x is not congruent to 0 mod 5. We have found this pattern through a very familiar type of problem that people see in competitions or in schoolwork, which is the last digit when I raise something to a very, very large power. But I wanted to dive in deep on this so that we can use this familiar problem that many people do to observe that there are deep patterns underneath that actually run at the mod 2 and mod 5 level. And we see these surprising things where if I take powers like squares and fifth powers of numbers, they are always themselves. This is the beginning of an interesting theorem we'll talk about next time.